Picture 11.92 gigabytes of text, a mountain of words. Before an AI can use it, a tokenizer breaks the text into small pieces and gives each piece a number. Those numbered pieces are called tokens. In Gigatoken's reported test, that text was already waiting in the computer's memory. A server using 144 physical CPU cores turned it into tokens in 0.4859 seconds, less than half a second. That works out to 24.53 gigabytes of text every second. Gigatoken's recorded rate was nearly 989 times the recorded Hugging Face rate in this GPT-2 comparison. Both tokenizers are meant to follow the same GPT-2 rulebook. So how can Gigatoken carry out the job so much faster? Look at the short sentence, "Tiny robots run." Before the tokenizer chooses its final numbers, it first splits the text into rough, word-like pieces. Each rough piece is called a pretoken. When the CPU supports it, Gigatoken's current GPT-2 path examines a block of 64 bytes together. A byte is one tiny slot of text data. One wide check labels the slots as letters, numbers, spaces, and other kinds, then marks where new pretokens start. SIMD means each instruction can work on many slots together. If the wide path is unavailable, or it reaches a tricky patch of text, Gigatoken uses a careful scanner that checks one byte at a time. That fallback is slower, but it protects the same GPT-2 rules. With safe cuts in place, the pretokens can move to the next chamber. Two copies of the same short pretoken arrive. The first copy still needs the normal BPE work, the rulebook that joins smaller text parts into final tokens. When the token numbers are ready, Gigatoken stores that answer with the pretoken. The next matching pretoken checks a fast memory table called a cache. The stored pretoken and its short token answer sit together in one compact entry, so a match returns the answer without running BPE again. Gigatoken also asks for a later cache entry early, before that pretoken reaches the front. In one author measurement using 1 gigabyte of OpenWebText, about 99.4% of short pretoken lookups found their answer in the cache. That does not mean every dataset behaves the same. Text with less repetition can miss more often. In this run, full BPE work was mainly the rare miss path. The common path was remembering an answer, not solving it again. The large text block is still one document. Gigatoken cannot cut it just anywhere, because a bad cut could split a piece that belongs together. It chooses only safe gaps where both sides can be encoded separately and still make the same token sequence. Gigatoken hands the large ordered chunks to a pool of workers, so several chunks can be encoded at the same time. These workers stay ready for later calls, and each keeps its own cache. That lets remembered answers remain useful without workers fighting over one shared cache. Each worker writes a flat row of token numbers for its chunk. When the first chunks finish, Gigatoken can start placing their rows into the final output, even while later chunks are still being encoded. It keeps the original chunk order, so the pieces rebuild the same token sequence without saving all the assembly for the end. The first condition sits at the starting line. All 11.92 gigabytes were already waiting in memory before the stopwatch began. The timer covered encoding those bytes and building the token result, but not reading the file from storage. So 24.53 gigabytes per second measures the encoding step after loading. The comparison also gave the three tokenizers different kinds and sizes of input. Gigatoken received one 11.92 gigabyte buffer. Hugging Face received 100 megabytes already split into strings, and TikToken received 1 gigabyte split the same way. The recorded rates belong to those chosen paths, so this was not a same job race. The benchmark ran 3 rounds. The stored comparison kept the complete round where Gigatoken reached its highest throughput. That is useful for showing a peak, but it is not the same as choosing the middle result. A separate Krabarina rerun used a 174 megabyte OpenWebText slice on a virtual machine with 4 logical CPUs. Gigatoken ran 26.2 times the TikToken rate and 83.4 times the Hugging Face rate, and its outputs matched Hugging Face on all 35,356 documents in the reported validation. That does not reproduce 24.53 gigabytes per second or 989 times. It does support the broader direction that Gigatoken can be much faster. Now send the same 11.92 gigabyte text block through the finished map. Gigatoken does not change the tokenization job. It makes that job flow better by finding many cuts together, reusing answers it already knows, and keeping many workers busy. The important change is not a new token rule. BPE still handles pieces whose answer is missing. The gain comes from arranging data and memory around BPE, so the common path does less waiting and less repeated work. So the careful conclusion is this: Gigatoken can make large BPE batches that are already in memory dramatically faster than the tested tokenizer paths. The figures, 24.53 gigabytes per second and nearly 989 times the recorded Hugging Face rate, belong to the showcased server with 144 physical cores. They describe an impressive peak, not a promise for every tokenizer or workload. The rules did not become easier. The route through them became much better.